from like American football to school, but
Okay, so first thing I want to talk about is polynomial equations. Okay, polynomial equations. When we deal with polynomials, okay, kind of give you. You remember we're talking about linear equations, right? And we went through a series of this is a linear equation, this is an equation that is not a linear equation, that kind of thing. We would want to do the same thing with polynomial equations. I don't have anything written up here in regards to examples that we say yes, this one is, or no, this one isn't. But all your polynomial equations are going to look like this. Now, what I'm about to write, you're probably not going to like, but it is what it is. So this is a polynomial equation. Okay, we start with maybe 0 equals. Okay, I think the last class I put like p of x over here. And I wrote it as a function, but let's write it as an equation here. Now I'm going to write a, and then sub n. Okay, so that's just a subscript. It's kind of a last name that goes with a. And we're going to write x to the nth power. All right. That notation just tells me that whatever that coefficient is, it's paired with this x to the same exponent. Okay, so this might be that. I guess that's the way I say it is that's just an identifier to tell me which coefficient it was. Does it go with the first term? Does it go with the second term? So when you see it, maybe a little bit better when I write it this way. A. The next one will be a sub n minus 1 x to the n minus 1. Okay, so those subscripts of n minus 1, that's the same as the exponent n minus 1, right? So it's just an identifier to allow me to link together. It says this is the coefficient that goes with this x. Okay? So think about what this would look like if n was like 5. Okay, if n was 5, maybe this is, I don't care what this coefficient is, maybe it's 2. So you have 2x to the 5th. Okay, now this here, this a sub n minus 1 just means it's a different coefficient than what that was. Or it's potentially different. It could be still 2, but let's make it different. Let's make it 6. Okay? And now x to the n minus 1. Well, what was n? N we said was 5, right? So n minus 1 would be 4. And basically what's going on right here, and we're going to continue that generic equation here in a moment, but what we're doing is developing a rule here that says if I start with the 5th power, then I'm going to have the 4th power, the 3rd power, the 2nd power, the 1st power, and the 0 power terms following that. Is that all right? Okay. If I start with the 12th power, then I got 12th, 11th, 10th, 9th, 8th, 7th, all the way down to 0. Okay. And that's what this rule here is going to define for us. So I'm going to put one more in here. I'll say a sub n minus 2 x to the n minus 2. A lot of times that's not written, and when you look in a textbook, a lot of times they kind of stop with this one and then do what I'm going to do here in a moment. But I just want to put this one in here because now it would be, if n was 5, the next term would be x cubed, right? Okay. Now I'm going to put a 0 there because a lot of times, if I had just 0x cubed, are you really going to write that? Or is that going to show up in the problem that the author's already created? No. So you might jump from 2x to the 5th plus 6x to the 4th all the way down to like x to the 1st or x squared. And all that tells me is that the x to the 3rd or the variable terms that are in between just have coefficients of 0. Okay, so they vanished. But then we're going to put a plus sign here. And these could be, I got all plus signs, but they could be, I just want to say plus and I tell you some coefficient. That coefficient could be negative. So it could be plus and negative. We put these ellipses, and all those ellipses tell me is that the pattern that I've established so far with my equation is going to maintain all the way until I get to what I write next. So this is going to go, the next term in those ellipses would be a sub n minus 3, x to the n minus 3. A sub n minus 4 to the x to the n minus 4, or times x to the n minus 4. A sub n minus 5 times x to the n minus 5. And it's going to keep doing that, all right? But it's going to keep doing that, especially in this case here. Once I get to a sub n minus 5 times x to the n minus 5, that gives me 0 as an exponent, right? And essentially I just stop there, okay? So if I have x to the 5th as my leading term, then I'm going to have potentially 5 or less terms up here, And when I say less, it's because some of them have zeros as coefficients. So then this last one will be a sub 1 x to the first, because every time I will eventually get an exponent of 1, meaning that, if I subtract 4 from that, I'll get an exponent of 1, right? Okay? So that will show up somewhere within our equation. And then the last one I'm going to write as just a sub 0. If you want to write times x to the 0, you can, but what is x to the 0? It's just 1, so a sub 0 times 1 is just a sub 0, right? So that's going to give me something that looks like that. And now if I continue to kind of give me a specific example here, maybe it looks like this, 2x squared plus then maybe 3x, maybe minus 12. So a sub 0 would be my negative 12. A sub 1, x to the first would be my 3x, okay? This 2x squared would be somewhere inside those ellipses. Okay, we get the x cubed, kind of matching up with that one. Here's your x to the fourth, and here's your x to the fifth. Those are things that are polynomial, okay? Anything of that format is polynomial. What that means to us, if I look at this, and I guess I probably should say that n has to be a positive integer, okay? Or maybe we say a non-negative integer, so we can incorporate 0. But if n is 0, then this thing's just kind of boring. And a lot of times we're really focused on n being bigger than 3 or bigger. Because if it's 2, it's quadratic, which is still a polynomial, but we have maybe different techniques to talk about it. If it's 1, it's linear, still a polynomial, just got different ways of talking about it, easier ways to talk about it, discuss it. Is that okay? So you can't have like fractions as your exponents. You can't have negative numbers right now as your exponents. They have to be your positive integers. Okay. So if I were to write something like this, let's give me an example here, like 2x cubed plus 3x squared plus 1 over x plus 2. Okay. Start looking at this left to right, it starts looking polynomial, right? But what is this thing here? That's x to the negative 1, isn't it? Cannot have a negative exponent. So that thing would not be polynomial. Okay? And that's something, guys, that we need to be able to recognize and understand, because a lot of times throughout mathematics, when I get to a problem, the direction, especially in algebra, the direction a lot of times just say find x, find all real solutions, do something like that. It does not say, hey, remember this is a polynomial. Let that target, or you start using your procedures that you know that deal with polynomials. You're going to have to recognize that first, and then that implies to you the set of procedures you go through to solve it. You're not going to see an equation that has a radical. So, hey, this is a radical equation. Remember, you got to square both sides to get that radical go away. The direction's over there. It just says solve for all real solutions or something like that. So recognizing types of equations, hopefully then kind of signifies to us the procedures that we're going to go through. So we'll do a couple examples of this. Right now, we'll do like 3 examples of these polynomials, and really, guys, this is just an extension of factoring. Okay, we already know how to factor some quadratic equations. Now this becomes this power of 3. If that's the largest power, we call this a cubic equation. Okay, if it was a power of 4, I think one of the examples we see is a power of 4. It's a quartic. 5th power is a quintic. And then after that, we just say 6th degree, 7th degree, 8th degree, whatever. Even if you want to call this a 3rd degree polynomial, you'll hear me say that a lot. That's fine. But we don't have any tools yet to address that. Okay. If you guys remember last year, you did synthetic division, right? You did long division, and inside that, or kind of tied to that, is a process called the rational root theorem. You guys ever do that last year? The P over Q, that come to mind? Okay. That's how you factor just your traditional larger polynomials, larger degree polynomials, okay, other than x squared. But right now, we're going to make the assumption that we haven't seen that stuff, we don't know that stuff yet. So the only tools that I have are quadratics. Yeah, it's the only factor I know. So what we're going to try to do is see if we can kind of dissolve what we currently have down to a quadratic. All right, and that then will allow us to address what we've talked about in the last couple of days. So in doing this, first thing you do, it's factoring, okay, solve by factoring. Whenever you see a polynomial and you're asked to solve for variables, solve for x, that's the process you gotta go through, factoring, okay? Even when we start talking about rational root theorem or P over Q, that kind of stuff, that's still factoring. It's just a different technique. So what we're gonna do is we're gonna try to get everything equal to 0. Whenever we factor, everything's gotta always be equal to 0. So we're gonna x cubed minus 25x equals 0. That's what we want to do. Okay? Now at that stage, and I've written it over here on the board, it's kind of part of our hierarchy for factoring, right? We talked about last week that the first thing I want to do, no matter what degree the polynomial is, no matter how many terms I have, the first thing you want to do, because it just makes things so much simpler if this exists, is to bring out a GCF, a greatest common factor. Something that will divide every single term equally, okay? Or so that your quotient ends up being a whole number or a whole object, okay? Because I can divide by anything, you know, I can divide that thing by everything up there by x squared, but it doesn't really lead to anything useful doing that, okay? But I can divide everything by what up there that would provide something useful, x, okay? Now here's the thing, when we divide that x, we're dividing, and we're doing this on the left-hand side, we're dividing it out. You can't just let it disappear, okay? It has to stay, because we're just reorganizing things, and the left-hand side still has to be x cubed minus 25x. It's just going to be written in a different format. So if I factor an x out of x cubed, I'm left with x what? Squared minus 25x equals 0. Okay? And now, I still have two things, right? I still have two factors there, right? Just like all other factoring, we have now two amounts that when I multiply them together, I should get the product of 0, correct? Okay? What this tells me then, right now, is that x equals 0, correct? And that's a linear term, that's a linear factor because the power is to the first. But I have x squared minus 25 equals 0 as well, okay? That is a quadratic factor because of that power of 2. We want to break that down even further, okay? So what is x squared minus 25? Now that gives it, remember what I said at the beginning, is that we're going to try to dissolve the cubic down to something quadratic, or a component of it being quadratic. What does that thing factor to now? Okay, so we have difference of the perfect squares here. And now we have three factors that multiply together give me 0. And it doesn't really matter whether I have 2, if I have 3, if I have 38. If I have 38 factors and I'm multiplying them all together and they give me 0, what do I know about one or all 38 of them? They should be the what themselves? What do I know about each one of these factors if they multiply together and give me 0? What could that one be? That one could be 0, right? Okay. Now I can make the other ones 5 and negative 5, okay? But when I multiply 0, 5, and negative 5, what do I get? 0, okay? This one here is going to give me x to be negative 5. So I can take negative 5, 0, and negative 10, and multiply them together, what am I going to get? Still going to get 0, right? And the last one, x is equal to 5, so I can take 5 times 10 times now 0, and what's that product going to give me? 0, right? Okay, so those are my three options then for that cubic equation. Okay, and really what that tells us, remember we talked about this stuff graphically. You don't know maybe yet how to graph a cubic. Maybe you've seen them, but if I graph x cubed, it looks like that. Okay, if I graph 25x, that line right there. Let's see if I can adjust my axes so you can see all this stuff. Always do that backwards. I'm doing the way I would anticipate doing it. But if I zoom out, let's do it this way. If I zoom out, I gotta get to 125 to do this on the y-axis. So the black line is the 25x. The blue line is your cubic. Do they cross right there? Yeah. Okay. And they're going to do the same thing down here. Okay. At -5, x value of -5. So that should be, those should be your solutions. And you see as well that they cross here at 0, 0. Okay. If we're asked for the intersection points of that and that, you see -5, 0, and 5. Okay. So that's what's going on. If we did it this way, if we do what we did by hand, so we move the 25x over, okay, that creates a different looking cubic, okay? That cubic is going to look like that thing there. It's going to look like that thing there, okay? But now we'd be interested in where that crosses 0, right? If we zoom in, we cross 0 at -5, 0, and 5. Okay? So you can use those graphical approaches again to verify your solutions if need be. But that's the first type of kind of polynomial equation that we're going to deal with in regards to solving if you cannot use like if it's not quadratic, if you can't use the product sum technique or the AC method or something like that, okay? Because those only work for quadratic equations. All right? Okay, so this is another cubic. Okay, example 2 is another cubic, but I start looking at that, and not every single term can have an x brought out, right? Okay. Now, if I didn't have that 10 there, okay, so let's say that 10 disappeared, then would everything have an x in it? And then you'd want to pull that out, and what you'd be left with is an x outside and then a trinomial that is a quadratic, and you should be able to factor that trinomial, okay? But because that 10 throws a wrench into everything, and we can't use that technique. So this is kind of the next thing you want to do here. It says if the polynomial is 4 terms, okay, and there was no GCF, what you want to do is you want to try factor by grouping, okay? That's the next option, okay? Later on in later chapters, we'll talk about, well, what happens if there is 4 terms, but factor by grouping doesn't work, because it might not work. And that's where you would use the rational root and the P over Q stuff, and that could give you a potential process for factoring. Okay? So, we are going to group these, and when you group them, guys, and we talk about this with the AC method, group that back set of two terms. Group them so you include that negative sign or the plus sign in that group. Okay. Another thing that's important in regards to grouping, you need to make sure that they're in descending order. If that polynomial is not in order, because I can give you like x cubed plus 10 minus 5x squared minus 2x equals 0. And if I just haphazardly start grouping the front 2 and the back 2, there's nothing that's going to come out of those front 2 that makes this a factorable problem. Does that make sense? They have to be in descending order. Okay. So when they are in descending order, let's look at the blue section. What is in common? What happens with those blue? What do they have in common? X squared. Okay. So bring the x squared out. Now I know that probably 95% of us know what we're doing here and why we can do this. But I know there's always 1 or 2, 3 people maybe per class that struggles with what is left over when factoring. Remember, all factoring is, factoring is a fancy word for what? Dividing. Okay, we're just dividing out an x squared, right? So when I have x cubed minus 5x squared, and I factor out an x squared, okay? Remember what that means. That means that what is left over on the inside of the parentheses is that quotient of x cubed divided by x squared. And then this thing here, minus 5x squared over x squared. Okay? And what that means to us, guys, hopefully we know our laws of exponents, but breaking it down even further, x cubed means that, right? X squared means this. Okay? So that is a factor of what there? 1. That is a factor of 1. Factor of 1. Factor of 1, right? So you're left with 1 times x minus 5 times 1, right? So what's left in my parentheses is x minus 5. Okay? And that's the logic of why we can do that. And you guys know the shortcuts and all that kind of stuff. But sometimes, every year, I have a handful of people that get stuck on what should be left in there. A quick check, multiply that through, distribute that back through, and you should get x cubed minus 5x squared. Okay? Now, the next thing you're going to do is look at the red stuff, and what can come out of the red stuff? -2, okay? The reason I want you to put that parenthesis around the negative is because a lot of times people will just take a 2 out and make it positive, and that throws everything off. It throws the signs off in that second grouping. So if I take a -2 out of this, what are you left with? Yep, just x, and then you take that out, you're left with -5. And what I say, if I don't put that -2x in the parentheses, a lot of people take a +2 out, and then they're left with -x plus 5 on the inside. And they say, well, that doesn't match up with what the other set of parentheses is, so I'm wrong and this doesn't work. Where it's just you missed a negative. Okay? That could also come out. So we get equals 0 here, right? Does that look just like what we did with the AC method when we factored quadratics? Is that the terms on the inside of the parentheses were the same, so that's a factor. So x minus 5 is a factor. Then we have the terms that are on the outside, the x squared and the -2, and that's a factor as well. Okay? Now, we have a linear factor x minus 5. We also have a quadratic factor x squared minus 2, right? Can you factor that x squared minus 2 further? Yeah, you guys know that, if I can say, let's do it this way, x minus 5 equals 0, x squared minus 2 equals 0. I'll go ahead and set that up this way right now for this example. Because I look at that, and there is no b term, right, in that quadratic. Okay, it's x squared, no b term minus 2, so that means I can use the square root method to solve for x. I can add 2 to both sides, and then I can take square root of both sides, right? And that set of solutions, there's 2 solutions there, positive root 2 and negative root 2. Both of those will give me solutions. When I plug in here, it'll give me 0 back. And then over here with this one, I get x equals 5. So those are my 3 solutions for this particular question, right? Okay. Hopefully, maybe Sam, we'll talk about this in a lot more detail later on. But as you start seeing and looking at your polynomials and your quadratic equations, your cubic equations, your quartic equations, when there was a power of 2, what were the possible answers you could have? 0, 1, or 2, right? Okay. When there's a power of 3, the maximum number of answers you have is 3. Okay. Now we'll talk about some discrepancies or situations that occur if I don't have 3. Can I just have 2? Can I just have 1? Can I have 0? And we'll talk about those things as we go through other chapters. But right now, if I see x cubed, I could have 3 answers. X to the 4th, next question, could have 4. Does that make sense? Okay. So that's something to think about as we're moving forward. Another way of doing this one here, x squared minus 2. This might be something that we use later on. So I think experience it now might be a good idea. It's not a difference as perfect squares, right? But it is a difference. Okay. So I'm going to write it this way. I should still be able to take x squared minus 2 and write it like that. Okay. Now, when it's perfect squares, we like that to put an integer in those 2 locations, right? In the binomials. Okay. So if it was a 4, we like to put a plus 2 to minus 2. If it was 9, plus 3, minus 3. But 2 is not a perfect square. But there is still a real number that I can multiply by itself 2 times to get 2. What is the number I can multiply by itself 2 times to get 2? Don't think integers. Don't think rational numbers either. What number can I multiply together to get by itself 2 times to get 2? radical 2. Do you guys agree with that? Is radical 2 times radical 2 just 2? Okay. So if I write it that way, if I factor x squared minus 2 that way, I got my, what is it, x minus 5? Okay. So there, we can break that equation down that way. But again, it still gives me the same set of 3 solutions, right? Okay. But when we get to later sections in, I think, chapter 2 or 3, that is something that we want to pay attention to. Okay? So I think seeing it now, first time might be useful. Questions on that one? All right, so hopefully you see that through a few strategies, a few initial steps, it breaks the problem down to something we're more comfortable with, right? We should be more comfortable with quadratics than we are with cubics. We should be more comfortable with quadratics than we are quartics. We should be more comfortable eventually with cubics compared to quartics, okay? So the lower we can make the degree inside our factors, the greater the comfort level should be. This one here, if I look at that, it's a 4th degree polynomial. Okay, there's only 3 terms. So if there's only 3 terms, maybe I want to start looking at my list of procedures here, and GCF's the first thing I look at that. Is there a GCF up there? So every single term has something that I can factor out. X squared, okay? So I factor that x squared out. Okay, x to the 4th divided by x squared is x squared. 4x cubed divided by x squared is 4x. 2x squared divided by x squared is 2. Okay, now, I look at that x squared, and a lot of times you guys aren't going to write it this way, but it's x times x, right? All right, now, with WebAssign right now, you know, I'm going to get 0 from that solution there, correct? I'm going to get 0 from that solution there. Right now, all I have to do is type in the 0 one time, okay? But we should also know and be able to start recognizing that that is a double root or a double solution. So that should tell us something graphically. But this thing here, x squared plus 4x plus 2, a quadratic equation that hopefully maybe we are comfortable solving. I try the product sum technique. 2 numbers multiplied together are going to be 2, have to be 4. Do those exist? Nope. Okay, so I can't use that. So that kind of just brings me to what other option? Quadratic formula. Okay, so I want to say x is equal to the opposite of b plus or minus b squared minus 4ac. So 4ac was just going to be an 8 eventually, and then 2a on the bottom. So that's going to give me radical 8 underneath the radical, right? Or radical 8 in that second part, okay? What's radical 8 simplified to? 2 radical 2. So I have negative 4 plus or minus 2 root 2 all over 2. Okay, and that's my solution for x. Now, what can I do there? I can simplify. What can I take out? I can take out 2. Take out 2 there, take out 2 there, take out 2 there, right? So it gives me negative 2 plus or minus root 2. I think I talked about this with you guys last week. But if I'm dealing with something like negative 4 plus or minus 3 root 2 all over 2. I think the first thing I'm talking about is that root 2 is not 2, right? That root 2 is representing 1.4144. Okay, on forever, never repeat, never ending. So that number, right, that's a symbol for something different than that. Does that make sense? Okay, so they're not going to cancel. There will be cancellation here, right? Is there cancellation here? No. So I can't just do that and rewrite my answer as negative 2 plus or minus 3 root 2. That is not true, okay? Because this is the common denominator for this fraction. Okay? And if I break it apart like that, do you see now that that is negative 2? And I can absolutely write that as negative 2. But is there any cancellation here? Because remember, this is 3 halves times root 2 over 1. There's no cancellation there, right? So I can only write this as 3 root 2 over 2. Those two things are, this is the right answer. And those two things are obviously different, right? So you can't just say, well, I'm going to cancel with what I want to cancel, because that works there. It's got to be in all three. That's why we can kind of shortcut it here, because that factor of 2 is in all three. I get -2 plus or minus √2. So those are my options for x. Those are two solutions. X equals 0 and x equals 0. Now again, like I said, you're probably not going to write both those down. This was a 4th degree polynomial, right? How many solutions do we really have there? We have 4. Well, if I count them all, if I count 0 twice, right? Okay. But 3 if I only count once. So we'll talk about that multiplicity of roots and stuff like that. I'm going to send you guys a PDF. I've already done it. There's like 32 questions on there. It's not due tomorrow. You can't even do all of them, but some of you can. So search through some of them. Get a start on it. You probably do, I don't know, anywhere from 8 to 10 of them. And we'll pick up this stuff tomorrow.